catch up on it.
Yes. So Thomas just asked if there's meant to be an green box.
Yes, it is. Right. Now, osmosis. Well, what we've done is we've done diffusion, we've done osmosis, right, and then we're going to be going on to something else called active transport. What's osmosis?
Osmosis. Did we do this last lesson?
We did.
Oh, there was we like the diffusion between like water molecules and like there's a less percentage of less percentage of water on one side, and so the water tries to diffuse itself, so it spreads off evenly throughout both sides. But the holes in the wall are small enough to let the water molecules in, but the sugars can't get through. So it's partially permeable membrane.
Very good. What you've done then is you told me absolutely everything to do with it, right? And it took you about this long, right? And the actual definition itself is osmosis is the movement of water particles from a high concentration to a low concentration across a partially permeable membrane, right? And the main example that I then gave was where you had kind of like a piece of potato in there, and I had 6 sugars, 4 waters inside there, and if that is then 10 waters, or 100% water, what's going to happen to that potato?
It's going to make smaller. You have to, not bigger, but you have to add, no. You have to take some from that 10 to make it even.
Yeah, so what it does is osmosis is the whole process of actually evening out all the waters. So if you've got 4 there, 10 there, what will happen is 3 will go in to make 7 there, 7 outside, and that piece of potato then gets bigger. Okay, if it's the opposite direction, then the piece of potato will then get smaller. That's what we then talked about last time. Okay, now what we also need is, right, we need some terminology. Okay, so in your green exercise books, if you wouldn't mind getting those out for me, please. I'll just give you a green one, haven't I? You are, sorry? I don't think I've got. I haven't got any books at all. You need to have a good look at home, because the chances are it's probably at home. Okay? I mean, if you want to have a look around, I'm quite happy to do, but you're not going to find anything, I don't think. Right.
Sure. So,
Yeah.
No, we can't
can you
see
move the camera to the left a bit? We can hardly see it.
That's lucky, isn't it?
Everybody's
just read sideways.
Right, well, most of the time I'm going to be standing right in front of the screen there. Right?
Thanks.
Right, yeah, that's better.
That's better.
You just made it worse.
No, it's not. That's better.
No, I can't see it.
You just made it 10 times worse.
So,
Just wait till it's blurry. It's a bit blurry.
Well, get some glasses.
What?
Right, I'm going to be standing here, right? Theoretically, I shouldn't be using the camera, right? Because I don't think many teachers do. All right. So I'm just going to be Lewis. Mute yourself now, please.
Okay.
Thank you. Right. Now, in your exercise books, right, the green exercise books, we're going to go through osmosis. It's going to be osmosis and animal cells. Right. Now, there's 2 bits of terminology that we need to know about, or 2 key words. Now, we talked about osmosis, right? And then Dominic then told us that if we then put something, it was, who was it that said? I can't remember who it was that said, right? That if we put a potato into water, pure water, water goes into it, it then gets bigger. Okay? Now, osmosis and animal cells. There's 2 cells here that we've actually got, and what they are is, they are red blood cells that look a bit like that. Okay, a red blood cell. Now, when red blood cells get put into something, there's 2 words you need to know about. You need to know the word lysis, and you need to know the word crenation. And basically, what that means is, if you put a red blood cell into pure water, what happens to the cell? Right? If you've got 100% pure water outside of the red blood cell, which direction is the water going to go? Loads of water outside the red blood cell. Yeah, they're going to even out. What's going to happen is the water's going to go in. Okay? Now, if water goes into a red blood cell, what it does, it swells up and bursts, and the name for that is lysis. Okay? The second thing is, if you put a red blood cell into very low percent water, what's the water going to do? It's going to come out. That is called crenation. All right? So, just to repeat that again, right, and everybody needs to then write the title in their exercise books. Osmosis and animal cells. You then need to explain that if you put a red blood cell into pure water, water goes into the red blood cell, it swells, pops, and that's called lysis. Okay? So in the exam, here's the mic turn around to you and say, what is lysis of a red blood cell? You would then have to say, it is where water has entered the red blood cell, it is swollen and popped. The other word is, if you put a red blood cell into like strong salt solution, strong sugar solution, water comes out of it. And what it does, it shrivels up. That is called crenation. Right? And again, the exam question could be, what happens in crenation with a red blood cell? Okay, so just need to write your own notes down. Come on. Yeah, you need to, that section is lysis, that section is crenation, right? But don't just write it, read it down and say, if you put a red blood cell into 100% water, it swells, pops, and that's called lysis. If you then put a red blood cell into strong sugar solution or strong salt solution, it shrinks, and that's called crenation. So this one is a high sugar or high salt solution. That one is a high water solution.
Sure. So do you know the like actual red blood cell thing, yeah? So do you know all like, because that's a red blood cell too, isn't it?
Yeah.
Yeah, so is it only that dark red because of the blood in it?
Yes, the hemoglobin.
So the
Yeah.
actual capsules is like a pink.
Yeah. So what they are is they're kind of like a red colour, right? So what they'll be is they will be. There's me clicky thing on. What a red blood cell normally would be is that sort of colour. It'll be like a red, possibly not dark as that. Right? If you imagine that it swells, right? What's going to happen to the colour? It's going to dilute a bit, isn't it? The colour, yeah. Right? So what happens is it goes to that colour, swells. Now you get to twice the size of it normally be, and then it pops.
You get that big?
Well, it's not that big, right? But if you think that on the end of that pen there could be 20,000 red blood cells on the end of that pen, right? So you're never ever actually going to see them physically. It's the same as if you cut yourself, right? If you cut yourself, get nosebleeds next to the sink, right, and water goes into the sink, right? What will happen is you'll see the red blood cells spreading out, and if you could actually look at them microscopically, they will be popping, right? They'll literally be dying. Okay, and that is lysis. And the word lysis actually means death. I don't know which is English. Right, it's probably Latin, some Latin derivative of some sort. Well, crenation is shrinking, but I don't know the actual.
Isn't that when you get
cremated? Yeah, it's slightly different.
Oh, I thought you said coronation. Was that in that where you get married?
All right, or cremation, right, where you get burned. But yeah.
You know when you put yourself and you pour like that thing on, why it's not bubbling, why?
What, sorry?
You know when you put yourself and
Yeah.
you pour something on it, some alcohol, why is it all like?
I don't know, maybe it's the scarring underneath. I'm not quite sure. Right, so what everybody should do, and those people at home as well, you should have written the osmosis and animal cells as your title. Right? Then all right? And obviously the way that I always do this is you're going to write your own terminology words down. If you put a red blood cell into 100% water, it swells because of osmosis, it bursts, and that's called lysis. If you put a red blood cell into very strong sugar or very strong salt solutions, water comes out of it by osmosis, and it shrinks, and that is called crenation. Okay, should all got that down now. Okay, let's just not talk about it. Okay, again, this isn't a copy job, right? This is, you make your own notes so you understand it in the future. Okay, right, moving on. Right, we need to move quickly. Again, it's not just a copy job. Right, now what we've done then is we've done diffusion and we've done osmosis. Dominic told us about osmosis, right at the very start. Osmosis is the movement of water from a high concentration to a low concentration across the semi-permeable membrane. And what's the key word in osmosis? Water, right? Water. Anything to do with osmosis is always water, nothing else. Diffusion is then everything else, okay? So a smell diffuses, right? And what's the definition of diffusion? No, you. Go on, Ali. Diffusion, right? So if I spray the deodorant can, right, what do those particles do? What? They split up, right? But diffusion is the movement of particles from a
high concentration to a low concentration.
yeah, and this time there's no semi-permeable membrane because it just happens all the time. Okay. Now the third one is something called active transport. Okay, so now subheading in your exercise book is now active transport. Okay. Now I said previously that diffusion and osmosis are passive. Passive means no energy. You know, passive means they just do it. Right? What do you think active transport needs?
It's unpassive.
Unpassive. Okay, yeah, active is unpassive, so if it uses no energy passive, what's active going to use? Energy. Right? Now, what I've done here is I've then put active transport, right? Protein carriers in the cell membrane pick up particles and move them against a concentration gradient. All right, so that is kind of the same as, right? I spray a deodorant can, all right, and it spreads around the room. Active transport then is when I suck it back in, right? It's going against the concentration gradient, so it's going from low concentration all around the room to me. And what have I used up? Nope.
Yes, sir.
No.
Right. Right, what have I used up? Shut up. Right?
Sorry, sir.
What have I used up? Good. Right?
What?
Right.
You think?
Oh,
It's not rocket science.
Yeah. Just stay muted at home, please. All right? So for me to actually suck that deodorant back to me, I've got to use something up. Energy. Okay? So your subheading now is what is active transport? Right? I then highlighted the most important thing about active transport, which is protein carriers in the cell membrane pick up particles and move them against a concentration gradient. So basically, that means going from low to high. Yeah, write that bit out, and then underneath it is low concentration to high concentration. And if you remember, diffusion is completely opposite. It's high to low.
Is the working Wilson?
Good, yeah.
It's just to take a picture of the results.
Okay.
Just 2 seconds.
Yeah, that's fine. Okay, so to just repeat myself, right, sometimes I need to do that, right, it's my feminine side, okay, is,
How's that feminine?
all women repeat themselves, I'm sure, that's okay.
I don't talk constantly myself.
Well,
Well,
she don't even know what she is.
yeah, she said that again.
Right. So, what you should be writing is, what is active transport? We've done osmosis, we've done diffusion, they are passive. Active transport is that red bit, but it is now low to high concentration. All requires energy. All energy. For all the others, but there's no energy. Can you see it right now?
Yeah. I'm getting contacts.
Okay.
I'm having a Saturday.
Yeah, you see it, then you should get contact.
Just gonna go and see what it's saying and then get the rest of it. Because these are all raw and I burnt them.
Quite expensive.
Well, these are free, I'll get my free. That's the first time for you. How old are you till you stop being a kid?
18.
Oh, I'm 16.
No, depends what you do. If you drug temptation, it's 18. But you're obviously on the bus. If you're on a bus, if you're 16, 16
And the train.
and train any form of transport.
Not taxi, but
No, obviously not. Right, so that's active transport. Okay. Next little thing, right, that we're going to do, right? It's going to be a little task that I want you to do. All right. We've done about diffusion, we've done about osmosis, we've done about active transport. Down this right-hand side here, right, what there are is there's different things that need to go into each one of those individual circles. So, for example, if I circle that one there, right, involves water only, it is osmosis. So you're going to put it in that section there. Okay? If this one here, if I just underline this one, high to low concentration,
Diffusion.
it is diffusion, correct?
So you put it in the middle.
So that one then goes there.
Yeah, no.
Okay. Right, so it's like your Venn diagram that you may well get in maths. Okay? So what I'm going
So we
to
can't
want
see.
you to do. Why?
Well, look.
What can't you see? Can you not see the screen?
No,
We can't see the text.
You got one.
Who is it that taught then? Who couldn't see?
The diagram
The
thing
right-
to the right.
Yeah, the right on the table.
We can't see the text.
Can't see out.
Turn your screen sideways.
I've got my screen sideways. I just can't see.
I still can't see you. Sideways.
Right, yeah, I can't see out.
Millie.
Millie can't see. What can't you see, Millie?
The words on the side.
The table.
Like, we can't see the writing thing there, so.
Yeah.
Is it too small?
It's this small, yeah.
So you can see the circle.
No, we
Yeah,
can see
we
the
can't just see them words on the side.
We can see everything but that table.
Right, okay, I'll try and make the table bigger.
Yeah, it's just a bit blurry.
Do we draw the thing ourselves there?
Yeah, so what I want you to do is, you can start by drawing 3 circles like that, and then what I'll do is I will try, probably very badly, to make that table a bit bigger.
Bigger.
Is that better at home?
Yeah, that's fine now.
Yeah,
All right, nice.
Yeah.
Right, so So literally, what you're going to do then is you're going to do your 3 circles, right? And in your exercise books, do them reasonably big, right? Because obviously you're going to be writing these words in them, all right? Do your active transport at the bottom, right? What was at the left there? What was top left?
Diffusion.
That was diffusion, and then that's osmosis, right? And then just write each phrase into each individual one, right? And then what we'll do is we will then have a look, right? And if you need to move any of them, right, then maybe just do something you're unsure of in pencil before you do it. Okay? And then what I'll do is I'll judge it from people in the class about when you should have finished at home.
I can't do circles.
Okay, let's have no talking in class, please.
So it's the part one animal thing.
What?
What's the part one?
Active transport.
So can I just do little like subheadings?
You can if you want, right? I quite like the idea of the Venn diagram because then because one of them is going to be smack bang in the middle there.
I'll put all
Which one's passive? Where?
Passive, what does passive mean? Passive means passive. If somebody is passive, right, what they will do is they will just kind of sit there and just do very little, right? Whereas somebody that's active, right, like yourself, you're active, well, aren't you? Right, you're moving around all the time, and you're active outside school, right? Somebody that's passive will just be sitting there doing nothing. Right, so which of those 2 or 3 just happen? Osmosis does because it's the movement from a high to a low, and diffusion is high to a low. So active transport is completely opposite. It isn't passive, right? It uses up energy.
So,
Hello?
you know where it says is passive, would that be diffusion because it doesn't need any energy?
Yeah, and? Osmosis doesn't need any energy as well. So if you get in the bath, water goes into you, right? But you can't get anything back to it. It's passive, so passive is the gap in between the 2.
Against a concentration gradient.
So do they all require energy?
So again?
They don't all require. So They don't all require energy, do they?
No, which one requires energy?
The-
Active transport, active is energy, just that one. So the energy one is that one.
So what does turgid mean?
Turgid means swells up. All right, so in a plant, turgid means got bigger. Right, so
Osmosis.
why is that osmosis not diffusion?
It water.
The water, so it's the water's gone into a plant cell and it's swelled up and it's from turgid.
Would it be active transport out of that?
Oh, as soon as I mentioned the word water,
Yeah.
right, it's always osmosis. Right, don't even think about the actual what's going on with it. It is water is osmosis. Okay, that's the whole thing with it. Yeah.
How oxygen leaves a leaf?
Yeah. Oh, I guess. Is it going to be osmosis?
Not without water.
Right. And do you think a leaf is constantly using energy to get oxygen out? Right. So just kind of think about it logically about what it could be. Yeah, turgid means swells up, right? Well, I did all that did. Right, so turgid, one here, right, means swells up. Oh, who did that? Oh, no. Okay, so turgid there means swells up, right, gets big.
Where is it says occurs in nature, would that be osmosis?
Where's it, which one, sorry? Occurs in nature, right? Does diffusion happen in nature? So when I spray something, does osmosis happen in nature?
No.
Well, yeah, you jump in a bath, right? If you jump in a bath, you swell up. Does active transport happen in nature?
Yeah.
Yeah, so where's it going to be?
In the middle.
It's not bang in the middle. Okay, it's the only one, I think, right? That is all of them.
That's 80.
Yeah, if you think about it, is it water? No, it's happening kind of in root hairs, all right? Dominic?
I'm not sure about that.
This one involves transport of solutes, okay? That's quite a difficult one. Solutes is substances that are dissolved in water, right? So that there, solutes, means dissolved in water. So therefore, right, which one is it not going to be? No? Think about it. It's not going to be osmosis because it's dissolved in water, right? So what actually happens is, dissolved in water is diffusion and active transport. Okay?
Look active transport against the concentration gradient.
Yeah, so it's against the concentration gradient, yeah. Right, so it's a bit like going up a hill, right? So active transport is where you can go up a hill because you're using energy. Right, so it's downhill, that's with the concentration gradient. That's right.
It's fluid. You can tell. Because it doesn't happen any other time, does it?
Alright, what do you mean?
Whoever's at home, you can hear you tapping on the desk or something. Can you just mute yourself, please?
Alright, it's not me, slow down.
Okay, right. I'm going to go through them. All right, and what I'm going to do is, for those people at home, is I'm just going to do a line from each individual one, right, going to insert a section of the Venn diagram. So, Dominic involves water only. Osmosis. Okay, so that then should be in there, right? Osmosis is just water. Ali requires energy. Active transport, right? So that one then goes into there. It's the only one that requires energy. Ali?
Diffusion and osmosis.
Yeah, so it goes in that little gap there, right? Because what that is passive, means there's no energy used up at all. Diffusion osmosis goes into the bit in the middle. Olivia, movement of particles. It is diffusion, and I know you're probably a bit harsh actually because you've obviously just joined it in today. Come on. It's active transport, it's moving particles as well. What else? It's osmosis, right? So I told you a little porcupine at the start there, right? Where movement of particles, diffusion is moving particles. So if I spray something, right, particles move. Osmosis, water is a particle, and active transport moves particles in the opposite direction. So movement of particles is that little bit in the middle. Okay? Now my diagram's getting a little bit complicated now. Needs a semi-permeable membrane. Osmosis. Brilliant. Okay, that one goes into there. So osmosis is the only one that needs a semi-permeable membrane, right? And a semi-permeable membrane works by the size of the holes. Okay? Which one? What, high to low?
Yeah.
No.
Where does it go? There. That one there, right? I'm just going to clear mine now, right? So what we've done is high to low concentration is that little section there. Okay, so I'm just going to start it again because mine's then getting a little bit complicated. Okay, so if I draw my circles again. Okay, was that one? That's diffusion there, isn't it? Osmosis, active transport. Okay, so we're down to this one. Against the concentration gradient. Matia?
Active transport.
Brilliant. Active transport. That one there. Imogen occurs in nature. All of them. Right. So what occurs in nature is every single one of those in the middle there. All right. How minerals get into root hair cells. Dominic.
The diffusion, because it's like a mineral section of water.
It could be. Now that's probably one that you just need to think about. It's definitely not osmosis, because there's nothing to do with water. Right? Now if you've actually got a stem there, right, and it's got little root hair sticking out of it, what you've got to do is you've got to think about where the highest concentration of minerals are. And the highest concentration of minerals are actually inside the plant. So therefore, if you've got to take minerals from outside in, what are you doing with the concentration gradient? You've got to force it in, so therefore, minerals get into root hair cell is active transport. Okay, but I can understand why you thought diffusion. Okay? Ali, how oxygen leaves a leaf? Diffusion. Go on. All right, you got it right anyway. Fair enough. Ali, how water keeps plant cells turgid? Osmosis. Okay, because it's got water in it. Okay, Olivia, I'll skip you. Okay, involves transport of solutes.
Diffusion and active transport.
Diffusion and active transport, because it's got nothing to do with osmosis. Brilliant. Okay, and my diagram is a complete mess there now. All right. So people at home, you just need to make sure you've got the right bits in the right sections. Okay. If you anybody in here, anybody stuck on any of them? How are you to use them? Which one are you stuck on?
No.
Just following the diagram.
If yours in nature goes to which one?
Well, does diffusion happen in nature?
No.
Right, so when I spray that deodorant can over
But
there,
yeah, it wasn't real.
there's a middle lawn. What time's this lesson finish? Is it
3 o'clock.
3 o'clock?
Well, 5 to. But like, I'll go on
Your bell goes when?
5 past 3.
Not sometimes you don't go.
It
Don't
depends
go that
on
all
the
the time.
time.
3 years, it went at 3 yesterday. It wasn't the time.
So even no point was even being in school. There's like 6 people in lesson, and there's like 6 people in there.
13.
How long have you been in school, mate? I could not be bothered if you had.
I thought like you could be on some private tours.
Eating toast at
No,
9
eating or eating.
Eating toast at 3 o'clock.
Yeah. I was talking to him. That's why I don't know what eating.
Okay. Right.
I see.
Now, what we've done now is we've done diffusion, we've done osmosis, and we've done active transport. We talked all about them. Now, theoretically, what we should be then doing is a required practical. Right, now the required practical, obviously we can't do it, right, because we're not allowed to do practicals at all at the moment. Okay?
I've done that later.
Have you? Is it a good one?
Yeah. You don't know it's not doing practical, but she does that in the class so you can show us.
Right.
She does it so you can do that. No, she's not.
Yeah, she was. I remember, so she got these
Pardon?
So I remember it was disgusting, yeah, she got these tights and she got these mushy wee bits, and she mushed it through the tights to the
Oh yeah, I remember that.
to the centre.
Okay, right. Anyway, make the most of talking at the moment, because when everybody's back again, it'll be silent again. All right. Now, next thing we're going to be doing is I just need to start up the next topic. All right. We've done about osmosis. Now what we're going to do is we're going to go through the osmosis required practical. Right. So just rule off where you've done in your exercise books, please. Then I want you to write down the subheading now: osmosis required practical. Now, the way that we're going to do this is, I'm going to go through the practical at the front. I'm going to show you the video that goes through it. We're then going to do it as like a sort of practical write-up. Then you're going to do that required practical booklet with the GCSE questions that go with it. But it's all based on osmosis. Okay? And what you'll see is, as I'm actually going through this practical, we've talked about a lot of it already, and I've introduced it. So, title in your exercise books now is Osmosis Required Practical, right? And apologies if you can't read my writing particularly very well. The aim of the experiment itself is to investigate the effect of a range of concentrations of sugar solutions on the mass of plant tissues. So, aim is, I want you to write that please. So, aim is to investigate the effect of a range of concentrations of sugar solutions on the mass of plant tissues.
pizza. That's what it's not a pizza, it's more satisfying.
Avon can definitely be a business. The team that work with me, I call them my Avon Avengers.
The next.
Okay, right. So what you should have done then is you should have written down aims to investigate the effects of a range of concentration of sugar solutions on massive plant tissues. I'm going to start showing a video and we're going to run out of time, right? And we'll carry on with this next week. Is we're going to do the independent variables, dependent variables, and control variables. But we don't need to write those down yet, right? What I'm going to do is I'm just going to introduce the actual practical itself, okay? So just listening in or watch this for maybe 3 or 4 minutes.
Potato. And we'll talk more about different concentration solutions in a moment. What I want to do first is prepare my potato, my plant tissue. To do that, we have a cork borer. This is going to allow me to take samples of potato that are all the same diameter. And that's really important so I can compare my results more easily. So here is one cylinder. Now I'm going to cut 3 cylinders. I'm just going to set up 3 different concentrations of solution today. So 1 cylinder, 2 cylinders, and my 3rd potato cylinder. Notice these are all coming from the same potato. It should help keep my results more consistent with each other, easier for me to compare my results with each other. Now, what I want to do now is just going to cut the ends off. The ends of these, the potato skin, I'm just going to remove those. They are impermeable. They will not allow water into the tissue. That's not what we're looking for. This experiment is all about water either moving into the plant cells or out of the plant cells. And that's really what osmosis is. I've now got my cylinders. They are all the same length, which is fine. They're all approximately the same length. So again, helping me to compare my results later on. But the instructions ask me to measure them into 3 centimetre lengths. So I'm just going to go with that. But they're all about the same length, which is fine. So I'm going to cut each one. Now, I'm only using a ruler here. Not the most accurate way of measuring these, but we'll go with it. I'll talk about that in a moment. 1, 2, so that's again 3 centimetres. Get as close as I can to 3 centimetres while using a ruler. 3. So I now have 3. As identical as I can get them, pieces of potato tissue. What I now need to do is measure them very accurately, as best as I can. I'm going to measure both their length using a ruler and also their mass using a top hand balance. So the ruler, I can measure them, and that one is exactly 30 millimetres. So they are all exactly 30 millimetres. Now I need to record those results. I need to make sure that I know.
I'm just going to stop it there, right? So what we need to do is need to carry on with this next time, right? So we're going to be looking at the independent variables, dependent variables, control variables, the apparatus, and the method next time. All right? So people in class and people at home, if you want to start putting your stuff away.
How to you?
I don't want to speak.